So on to tonight's talk. We welcome Dr. Dirk Frobrick of the University of Kent. Dr. Frobrick runs the HOYS Citizen Science Project, which encourages amateur observers to participate in long-term research to help understand the processes of star and planet formation. I'm also pleased that several of our members contribute regularly to this project. During the talk, all attendees will be muted. Please do not unmute yourself. If you have any questions for the end of the talk, please submit them using the chat facility at the bottom of the screen. So I think without further ado, I'll hand over to Dirk.
Okay, so I just shared my screen. Does that work?
Yes.
Thank you. Okay. So thank you very much. I didn't know this is your first attempt, so I'll hope to do my best that these kind of meetings actually take off. So thank you again for inviting me. I would like to come in person again because it was very nice when I was there a couple of years ago, but there we go. So the talk tonight is in part about that citizen science project, but what I want to basically focus on is I want to give you an overview about star and planet formation in the context, of course, of our HOYS project. And our project, because I'm not running this project on my own, I started it, but I have a colleague in St. Andrews, Dr. Alex Schultz. He is running the St. Andrews Observatory. He's a lecturer at the university there. So we are the two main scientific people who use and work with the data, but there's a number of more and other people who work with that data as well. So as I said, the talk is going to be mostly 4 parts. I'm going to focus on explaining how stars and planets are forming to give you the context of what we are doing. Then I'm going to try to explain to you why we actually do this with the Citizen Science Project, and in particular how. And then I'm going to show you some results. That's a slightly larger section than the one before. And then very briefly, I will explain to you how you can participate. But fortunately, I don't really have to do this because you got several members in your society that actually already do that. So they can do this at another time. Okay, this is one of the talks in a series of talks. So you can see all the other audiences. I took a picture of all of them. Most of the talks, this is number 47. I've been actually there in person. I've talked now to over 1,500 people about the project, 5 cats as well and 2 dogs. And up to March, I did a lot of driving to actually get to these places. But now this is the 5th of the online versions of those talks, which is nice. I can have a drink straight away without having to drive afterwards. But let's start with the actual content. How do stars and planets are forming? This is it's going to be a very, very brief overview, simply because I run a whole lecture course on this at the university, and even that isn't really enough. So we're going to do this very briefly. And this is a basic sketch that you might have seen in this form or another at some stage, how stars and planets are forming. Stars form inside so-called giant molecular clouds. So these are large, very massive clouds of gas and dust, which are everywhere in the midplane of our galaxy and another galaxy, in particular all the spiral galaxies. They typically have masses of a few million to maybe even 100 million times the mass of the sun. So they're extremely massive. They're mostly made up of molecular hydrogen. That's where the name comes from, molecular clouds. So molecular hydrogen makes about 3/4 of the mass of those clouds. The other quarter is helium, and about 1% of the mass in those clouds is in small dust grains. So these are not the dust grains you find in your house. These are very, very small. They're about a micrometer in size, and they're typically either graphite or silicate. So those make up only 1% of the entire mass, but they're very important. This is essentially the material out of which you make the planets later on. Now, in those clouds, there's a lot of things in terms of physics that are going on. But if you actually want to form stars, there's only really one thing that you need, and this is a force that collects material to make the star, and that is gravity. So the only thing you really need to make stars is gravity. Now, there's a lot of other forces in those clouds which actually trying to disperse the cloud, and literally every other force is doing that. So there's things like rotation. So if you rotate the cloud very fast, you get centrifugal forces. That works against gravity. You can get high temperatures. So you know if you have a gas and you heat that up, the gas is trying to expand. So there's thermal pressure that's trying to work against gravity. There's other things like magnetic pressures as well. There's turbulent motion of material. So all these things are there, and they typically balance on average against the gravity in those clouds. But every now and again, in certain places in these clouds, you get regions where gravity is winning the game, where gravity by chance is the strongest force. So by chance, there's enough material collected in a certain part of that cloud that suddenly gravity becomes the dominant force. Once that happens, the cloud starts to basically collapse into itself. So the material just falls towards the center where gravity is the strongest. And this is basically the start of the star formation process. So first, you can kind of think of this kind of everything moves radially into the central point, which eventually will be the star. But very quickly, a bit more interesting physics happen. The interesting physics is called conservation of angular momentum. Now that might sound very esoteric, that's why probably a couple of people didn't come today. But you've all seen that probably on TV if you've ever been bored enough to watch figure skating. You can see people on the ice, they rotate, they have their arms stretched out, and then they pull the arms onto their body, and suddenly they spin much faster. And a similar thing happens to these collapsing clouds. They all rotate a tiny bit when they start, and the material is moving inwards, so it gets closer to the rotation axis. Let's say it's here where I'm moving my mouse up and down. And as soon as you move material closer to the axis of rotation of a system, the rotation rate will increase. So the frequency of rotation of that cloud will go up. Now, what happens is at the same time, if you rotate faster and faster in the equatorial plane of that rotation, you will get a centrifugal force. So force that is pushing outwards against gravity. That's basically what happens if you drive around in a roundabout very, very quickly. You end up on the outside. Basically, in those collapsing clouds, very quickly, the rotation becomes so fast that the centrifugal force is as big as gravity. And then in the equatorial plane, you can't actually have any accretion anymore. Because both of the forces are balanced, the material just stops. Along the direction of the rotational axis, there is no centrifugal force, so material can keep falling to the center. And what happens is, hence, extremely quickly, you get this flattened structure around what will be the star at some stage later on. That originally looks like a donut, but we call that a disk or an accretion disk of material. So this disk forms very quickly. You got that what will be the star in the middle. Material then from the outside can't actually get to the star anymore because it's rotating too quickly. So it settles on the outside of the disk. It slowly moves through the disk to the inner edge of the disk, and then it accretes onto the star. Some of that material that goes onto the star is ejected into jets and outflows, which I'm not really going to talk about today. But basically, every time you have a system where you have a compact central object that is accreting from a disk around it, you will get these jets and outflows coming out. So that can be a young star, like in what we are interested in. That can be a supermassive black hole in the center of a galaxy that has an accretion disk. So it's exactly the same principle. We simply don't really yet understand how exactly these jets are launched. We know they're there. There's loads of different theories, but we don't really understand that. We know it has to do with magnetic fields and the rotation that happen at the same time. What we are interested in is these disks. So over time, basically, that reservoir of collapsing material is either accreted through the disk onto the central star. It might get pushed away by the jets that come out because they plow through the surrounding material, might push it away. The star, or what will be the star in the middle, that also radiates a lot of energy, and that will also push material away. So that reservoir basically disappears, and then you're left over with just the disk, where there's still material being transported inwards onto the star. And it's those disks where the planets are forming. So you start with these 1 micrometer dust grains who make up the disk, plus all the gas and all the gas that you have. And in those disks, the dust grains start sticking together, and they become larger and larger until they are big enough, either by sticking or collisions, to grow into things that are massive enough to then actually start pulling material in and then form planets this way. So eventually, once you start forming the first planet, that planet basically stops the accretion process because no more material can basically go through the orbit of the planet. So material that is stuck outside, it will get to the orbit where the planet is, and then will end up on the planet. It can't actually go through really to a large fraction onto the central star anymore. So very quickly, the material in those disks is basically turned into planets, or accreted, or pushed away. So that is basically how stars and planets form at the same time. So we typically don't talk about planet formation as such, because it's intricately linked to the star formation process. That entire process is extremely quick, astronomically speaking. So the initial collapse to basically form that initial object here that will be the star later once it fuses hydrogen, that only takes about at most 500,000 years. And then we know from observations that these disks live typically a few million years, so on average maybe 5 million years. And hence you only have these 5 million years to start from these micrometer-sized dust grains to make planets that we see in our solar system and in all the exoplanetary systems that we have found. So this is basically what we're interested in, is this process, how you make planets. And one of the things in those dust clouds that I mentioned before is the dust that is important. And this picture shows you why the dust is important. This is a small cloud on the sky. The cloud is called B68. And on the left is a picture how that cloud looks like at optical wavelengths. So if you had a good enough telescope, this is what you would see with the naked eye. And you can see the cloud basically blocks the light of all the background stars. And it's actually, as I said, 99% of that cloud is gas. But if you take all the gas out and you just leave the dust there, it would look exactly the same. It's the dust grains which actually scatter and absorb the radiation from the stars, and basically in the optical, in this case, block it completely. If you go to slightly longer wavelengths, if you go to the infrared, then what you see is this is exactly the same part of the sky, just at infrared wavelengths. You can still see the same outline of the cloud, and the patterns of the stars are basically the same. But you can start seeing the stars through the cloud at infrared wavelengths. So they tend to look red. And the simple reason for that is the blue light from those stars is scattered much stronger than the red light. It's the same as what happens in our atmosphere. The blue light from the sun is scattered quite strongly. That's why it comes from all the directions. And the red light is scattered less strong. and that's why it tends to only come from the star itself. So this kind of scattering principle is the same in our atmosphere, which is one of the couple of reasons why the sky is actually blue. So the same happens in those clouds. You have a star here that you're trying to observe. It emits some red photons and some blue ones, but the blue ones are scattered very strongly in all sorts of directions. So they tend not to end up where you are trying to observe it on Earth. The red light is not really scattered or only scattered a bit. And hence most of the red light actually ends up in your telescope, which means the stars all look much redder than they usually do. So hence, if you would know how the light looks from that star, if the cloud wasn't there, then we can use the observed color of the star when the cloud is there to infer what kind of dust grains are there. Because if you change the size of these dust grains, the properties of the scattering, they change. So for example, if you put all the dust grains into bricks, very small planets, but it's the first step. You need to go through something that is the size of a brick to make a planet. Then these bricks would be much larger than the wavelengths of the light, and they would also absorb some of the light, but they would do this for all the wavelengths in the same way. So the light would still be dimmer, but the red and the blue light would be absorbed by the same amount. So the color of the stars wouldn't change, they would just look dimmer. Now, of course, we can't actually look around the cloud. We can't move the cloud away to have a look and then analyze these dust grains. But in our project, we actually use this effect, and I'm going to show you an example later on how we can learn about the size of the dust grains in these star-forming regions in our project. So, as I said, we're interested in how planets are forming. I'm not really interested in how to make Jupiter. I'm interested in planets like the Earth, the terrestrial planets. And one thing we know is they form very close to the star itself. So the Jupiter-sized planets, they typically form much further out. They might migrate in and end up as these hot Jupiters, but typically they have to form where Jupiter is, roughly 5 times the Earth-Sun distance, so 5 astronomical units away from the star. The terrestrial planets, they will form much closer in. So they typically form within 1 or 2 astronomical units around the star. So if we actually want to understand how that planet formation works for the terrestrial planets, what we need to do is we need to somehow look what are the properties and the structure of the accretion disk in the inner 2 astronomical units. That's basically what we astronomically, observationally need to establish. So how can we do that? Well, you can take one of the biggest telescopes, an 8-meter mirror in the best site in Hawaii, and you point it at some nearby stars to try to image these disks. Here are some examples of some of those disks. There's some scale bars. You might not see the size, but the size here is several hundred astronomical units. So basically 2-3 times the size of our solar system. In all these cases, the light from the central star has been blocked. So that's where the black circle is. That's where the light would come from the star. It's usually much brighter than the disk. So that has been blocked, so you can actually see the disks. You see some structure. There's some spirally structure, lots of filamentary things. But you can see if you do this even with an 8-meter telescope from the ground, there's no hope ever that you're actually going to reach the inner couple of astronomical units in terms of resolution. So this doesn't work. So if you want to study the very inner regions, there is simply no possibility to do this with current technology. Okay, at least from the ground. What about spending a lot of money? That typically helps things, at least if you believe the government. So the first thing you can try, go to space, pay $5 billion for the Hubble Space Telescope. You pay another $500 million to repair it because you put the wrong mirror in. And then you point that at the nearest young stars because that's how you get the best resolution. And you have a look, can you see these disks? And here's a couple of examples on the left, pictures from the Hubble Space Telescope. So the young star in the top left picture in HH30 is actually hidden right where I have my mouse, you can't see any of the light from the young star. What you see instead as this kind of shadow is the disk of that system around the star, and we see that system edge on. And the disks, they're not flat, they don't look like Saturn's rings, they're flared. So the further away you go from the star, the thicker they become. That's why this kind of shadowed area looks like this. And the light from the star will basically bounce off the surface of these disks and then towards us as the observers. And that's why you see these kind of two kind of bowl-shaped scattered light pictures. So that the white light here is the scattered light from the star that is hidden basically behind the midplane of the disk. The green thing is the jet coming out. There's another object here. Again, we see the disk edge on. There's no jet in this case, and you got the two scattered light cases in the same way. The same here. The star is hidden where the dark patch is. That's the disk where there's no light coming to us. And the yellow bit is the scattered light, and the green thing is the jet coming up. Now, again, there's some scale bars here. They're both 200 astronomical units long. So that's about twice the solar system, all the way to the Kuiper belt. So these things have the right size, but again, the detail you can see is not good enough. So the detail you can see in the Hubble Space Telescope for the closest stars, about 300 light years away, is about 35 astronomical units. It's quite good, much better than an 8-meter telescope, but if you want to study the inner 2 astronomical units, hopeless, no chance. So the Europeans decided to spend less money and build the ALMA interferometry. That's cheap, that's only 1 billion euros. And it uses basically radio interferometry techniques. And you can then basically do the same thing, point that at the nearest young star forming region, and take pictures of these disks at radio wavelengths. And again, you see the star is here in the middle, and there you see there's much more structure. So the resolution of ALMA is much better. It can actually resolve detail of about 5 astronomical units for the nearest young stars. And you can see there's rings here, there's gaps, there's rings of material, there's gaps that might come from planets or not, who knows? And you get much, much more detail. But as I said, the detail is limited to 5 astronomical units. So the inner bit, basically Jupiter's orbit, would be somewhere here in that system. The inner bit, we can't really study the structure of those disks to learn how the material kind of behaves and forms the Earth or terrestrial planets. So you can spend even less money. You build the VLT. That's another factor of 3 cheaper. It's about 300 million euros. And you can take near-infrared images of disks around the nearest young stars with an instrument called SPHERE. And that is now, this is not radio anymore, this is now near-infrared, so almost optical light. And the disks look like what you imagine they do. Here's one example where, again, the light of the star is blocked. You got this dark ring here where the midplane of the disk is. You see some of them face on. Again, there's rings and structures. Here's another very nice example. And if you're lucky, you might actually find things like that. So this bright point here around this young star, which is again blocked out, called PDS 70. This is actually a young planet forming in that disk around the object that's accreting mass. There's another planet hidden in that mess here up there. So there's actually 2 planets that orbit that star in this young disk. But again, the resolution you have is 5 astronomical units. It's exactly the same. So this planet is very, very far out compared to where our Jupiter is in our system. So the resolution of ESO SPHERE is exactly the same as ALMA. It's about 5 astronomical units. So basically, with the current technology, there's no way we're going to resolve the inner 5 astronomical units, except the way we do this. So this is not a picture we took. This is an artist impression how the inner accretion disk will look like. So you get what will be the star in the middle. You have the disk around it. There might be some structures sticking out that comes from magnetic fields or maybe planets. And one thing we know is everything in that disk will orbit around the central star based on the initial collapse and the rotation. So let's assume the bit that is closer to the bottom of the picture here is moving to the right. So if we monitor the brightness of that system, and we watch it from this angle, we have no chance of resolving anything. We just get the total light coming from that system. But if the material in the disk is looking like that and it's moving to the right, it will eventually move in front of the central star. What that will do is it will dim the light of the star. It will also redden it slightly if there's dust grains in here. And you get that blue light being scattered more than the red light. Over time, this structure will keep moving further to the right, and eventually it will not be in front of the star anymore, and the whole system returns to the original brightness. If there's a second structure, let's say, like in this case, there's another side of that, then you will get a second dimming event. And if you're lucky and the structure here survives for a whole orbit, then you will see it coming back. And then you can measure the period. And what that allows you to do, if you know the period of any of these events, then you know, because measuring the mass of that central object is easy, once you know the period, you know how far away it is and how fast it is traveling. Which then means if you know how fast it is traveling and you know how long it is actually occulting your star, you know how big it is, at least in the direction it is traveling. And the detail you can see in these structures is basically as small as the size of your star. Because as soon as the material moves further than the size of the star, there's a different bit of material in front of it and changes the light that you can see. So basically, with this timing of occultation method, you can get a resolution of structures in these disks which are basically the size of the star, and the typical stars are about 1 to 2% of the astronomical units, right? So compared to 5 astronomical units, we can do 0.01 astronomical units. So we are 500 times better in terms of the resolving power than the best instrumentation that we have and will have for the next couple of years. So in terms of how much better that is, I always use this example in all the talks in terms of resolution. So you know the size of the moon on the sky is about half a degree. That gives you a start point. So your eye can actually resolve structures which are 1 arc minute away from each other, which basically 1 arc minute, you know, is a 60th of a degree. And a resolution of 1 arc minute basically means if you have a car, a normal sized car, that's 5 kilometers away from you, then your eye can actually judge at 5 kilometers distance if there's just 1 light on that car or 2. So that's how good your eye is. It's actually reasonably good in terms of resolving power. The best ground-based telescopes, so these 8-meter sized telescopes, it doesn't really matter how big they get. Any ground-based telescopes is basically limited to about half an arc second. So it's 120 times better than what your eye can do, which basically means at the same time, the resolution you get on your car, you can park the car about 600 kilometers away, or let's say Edinburgh from where most of you are, and judge, are there 2 lights on or just the 1. With ALMA, these radio interferometry and sphere with the VLT, the resolution is actually 0.025 arc seconds. That means you could park the car 12,000 kilometers away, but that is basically any interferometry technique. That's the furthest you can park your car and judge basically are there 2 lights or just the 1. Now, for the nearest young stars, that resolution corresponds to the distance between Sun and Jupiter, those 5 astronomical units. Now, our technique, as I said, is 500 times more accurate, but it's actually even better than that, because all these techniques, these direct imaging and interferometry techniques, they only work at this very good resolution if the stars are very close by. So our technique is completely independent on the distance of that object, because all we do is we time, and we measure how long is the star dim. And as long as we can see the light from the star, it doesn't matter how far away it is. So in our project, most of the stars are actually about 3,000 light years away. And if we have a resolution of 1% of an astronomical unit, at 3,000 light years distance, if you translate that to the car, then that means you can park your car on Mars and still see with our technique if there are two lights on or not. So that is basically telling you how much better in terms of the resolution we can do studying the structures in those accretion disks. But we can do even smaller detail, and that is we can look actually at the star itself. So I told you that the inner part of the accretion disk, the material is falling onto the surface of the star, but it doesn't do that homogeneously. It does that along magnetic field lines. So it ends up hitting the surface of the star in very small spots. The material is falling extremely fast onto the surface of these spots, so create shocks, which basically create little hotspots on the surface of these stars. And you know, everything is rotating, including the star itself. So basically, if that spot, let's assume there's only one of them, if the spot is on the front, then you can see it. So the star will be slightly brighter than when the spot is on the back, where you only see the normal surface of the star. The young stars as well, they might have, sometimes they have actually dark spots similar to the sun. They can also have a mix. But basically, if that star rotates, you can see basically the spots and then you can't see them anymore. So we can use that. You basically get a modulation of the brightness of the light with the rotation period of the star. And we can use that technique to actually probe, not just are there any spots or not, we can actually measure their size and we can measure their temperature. By simply observing this star at several wavelengths, and I'm going to show you an example later on. So to summarize, what we're trying to do with this, monitoring the brightness of these stars, is two things, or two main things. We can look at the structure of these disks in incredible detail, very, very small detail, which we then can feed into computer models and test planet formation theories. And we can also basically map out the surfaces of these stars, after measuring the periods, we can look and measure the temperature and the size and the positions of these spots and see if and how they move around on the surface. That's basically what we want to do. And we want to do this with the same kind of data by simply measuring the brightness of these stars over time, over and over again. And we want to do this with these amateur sized small telescopes. This is ours at the University of Kent, but basically we want to use amateur telescopes for several reasons. A, we would like to do this for 25 years, because A, that gets me to retirement, and B, we want to probe the inner 5 or 3 astronomical units, and basically if you want to see if there's anything that's periodic up to 5 astronomical units, then it will come back about 3 times in those 25 years. So you actually know it's really periodic. And we also want to do this with observing it at least once, if not twice, every day, if you possibly can, at multiple wavelengths. So everything in your optical, including the hydrogen alpha filter. So if you want to do this with professional telescopes, you will basically get told that's a no. But all our objects are young nearby stars. We want to observe as many stars as we can. So we look at young clusters and we all keep them very close within 3,000 light years, that basically all these small telescopes actually see all the stars in those clusters very, very easily. And to give you an idea which targets we pick, there's about half of them. We have about 20 or so targets. All of these, many of them, you know, the Pelican Nebula, Rosette Nebula, the Elephant Trunk, the Orion Nebula cluster, the Christmas Tree cluster, the Cone Nebula down here, Cuckoo Nebula. They're all beautiful. And many of the amateurs take nice pictures of these objects anyway, because they look nice. We just want those pictures from everybody, and preferably over and over again. And then you can take any nice make any nice pictures out of them. We are really just interested in the data, because when it comes to making nice pictures, you're probably much better than us doing so. Hence, why do we do this as a citizen science project? Well, the picture on the left, this is not true today, I'm actually observing in parallel, so it's actually clear today. But typically, you know that if you're trying to observe from wherever you are, the chances are it's cloudy. Literally everywhere in the UK, this is the case. So in this case, this is from a couple of years ago, typical radar picture. This is where our telescope is, it's cloudy. But what you see is, in most cases, there's even some part in the UK that is clear each night. So you could sort of just move your telescope over every night, but that's a bit tedious, or you use all the telescopes that are actually already there. And this is what the map on the right hand shows you. This is basically a location map of every single amateur society in the UK, which basically covers the entire UK, other than where no one lives, apparently, in Scotland. So all the societies seem to be around the edges. The best sky, typically in terms of darkness, is here, but it's mostly raining, so there's no point. But the rest of the country is very nicely covered. And hence, that's why we're going around the amateur societies and basically trying to recruit people to observe when it is clear. And this kind of method should allow us to at least get one picture per night for each target. So how does it work so far? Well, quite well. We are now in year 5 of the project. We have recruited 70 people from 11 different countries. So there's a couple of location maps. So all the blue circles are basically locations of amateur telescopes. So yours is down here somewhere as well, your observatory. Around Europe, you got a large number of people in Spain. They got good weather. And then we have a fortunate guy who has a remote telescope in the Atacama Desert, quite helpful, clear every night, and a bunch of people in the US, which basically allow us to take a second picture every night because they're a couple of hours away from us. We are getting closer and closer to having actually 30,000 images submitted to the project. And we've now made about 140 million brightness measurements of stars in those pictures, which we can analyze. This is just a chart that over time, you see the years over, how many pictures we accumulated over time. So I've updated this yesterday. So hopefully by next week or even by Sunday, we're going to break the 3,000 picture limit. So, and what you've seen is the curve is slowly getting steeper. So we're increasing the number of pictures we're getting. Our goal, as I said, one picture per target per filter per night. We are about 20% there. So there's still a little bit of recruiting to do. So now some results, as I promised. This was the first test image from an amateur in Ashford in Kent. These are actually 3 pictures near the Christmas tree cluster, taken 2 weeks apart, so it's about 1 month, and the images are blinking, and you can kind of see there are stars that change their brightness. I actually circled them so you can see that better. So everything in a circle, your naked eye can basically tell, oh, it's changing the brightness or something is happening with the naked eye. There's this really bad one here that completely disappears in one of the pictures. But basically, what we do is we don't just do this by eye. We actually let the computer measure the brightness of every single star in every single picture, and we analyze all of them. And the computer will basically tell you almost all these stars, all the young stars in that picture at some measurable level change their brightness. You can't see that with the naked eye. So what the amateurs do, as I said, they observe, and I'll show you later how it works. But all they do is they basically send us the pictures. They tell us for what target it is. And then we do a little bit of calibration. So we solve the coordinate system for each picture. Excuse me. And we measure the brightness of all the stars, and we calibrate that into a reference system. We're going to go through this, save a bit of time. And once we have done the full calibration, then we can start actually analyzing young stars and see what we can learn from that. And I'm going to show you 2 examples of this. The first star is called V1496 in the Pelican Nebula. And you can have a guess where it is. I show you there, it's this one. Looks like all the other ones for some reason. What I can show you first is how does the light curve of that star look like? But this time, I only show you about 2 years of the light curve, taken only with our observatory in Kent. So this is time on the x-axis, on the y-axis is the magnitude, the brightness, and the green points is the green light, red points are the red light, the black points is the infrared light of the star itself. What you can see is the weather in Kent is reasonably good. So basically we observe that field every time it's clear. What you see, that star is highly variable, so it changes its brightness by about 2 magnitudes up and down. And if you actually look careful, there seems to be some pattern. So it seems to go regularly down every about 30 days, but it's not very clear from the data set. So what we then did 2 years ago, we asked all our participants to observe this target field every night for 6 weeks. And this is the light curve that you get for just 6 weeks. Again, it's the same color coding. Now I've also added the blue image, the blue filter here, and some other filters on the bottom, but you can ignore those. The main thing to see is this is 60 days. This is 2 years, and you can count them if you want, but there's more data points in those 60 days that we get with the help of all the amateurs than we had in a whole 2 years with just one telescope. So this basically shows you why it is important to use this collaborative effort from the amateur astronomers like you are to help us to get a much more detailed light curve. So you can see here there are dimming events, and I'll show you in a bit that they are periodic, but you see the period we find out is about a month or 30 days, but there's very small things. There's these little dips here that only are about a day long. So each of these groups here of points is about 1 night apart. So you see a really fine structure. And in this case, it's material in the disk moving in front of the star, and you can really study the disk in great detail by having all these little wiggles, which are all real. These are not noise in the data. So it's an incredibly good data set that we can get with this method. So as I said, one thing we did, we studied the periodicity, we calculated the periodogram, and then you can simply, what we call phase folding the light curve. So you simply plot the light curve. You start at a random date. You plot the first 31 days, which is the period, and then you start at the beginning again, over and over again. And then what you see is this kind of phase folded light curve. Now, if all these dimming events were exactly the same, you should actually see not much scatter here. You should see some kind of normal behavior. In this case, we don't. What we see is at the beginning of the period and the end, so it's 0, 1, and we plotted the second one, the star is always bright. But when it is going through those dimming events, every time it does a dimming event, it does something different. So sometimes it doesn't dim a lot, only by about half a magnitude. Sometimes it dims by about 2 magnitudes. So basically, within these 30 days, the material is coming back, but the material that is in front of the star when it comes back is completely different every time it comes back. We can also study how does the brightness and color change. So I've plotted basically the magnitude or the brightness of the star on the y-axis here for every measurement we have, and the color. So blue things are on the left, red is on the right, faint is on the bottom, bright is on the top. And what you can see is if you plot all the data points we have for that star, when the star gets dimmer, it gets red. That's kind of what you expect if you have these dust grains in the disk. They move in front of the star, they redden the starlight. I told you that at the beginning. But the green line is basically how the data behaves. That is what we have fitted to the data. If you have normal dust grains, like in those interstellar clouds, the star should follow either the blue or the orange line, or somewhere in between. That is the normal dust grains we have in interstellar space, but it doesn't do that. It does have a steeper behavior in this diagram, which basically means the dust grains have started to grow. They're bigger than what they started with from the interstellar medium, because you know, if you make them very, very big, I told you the color will not change. So if you have bricks, the star would simply dim up and down without changing the color. So the steeper this behavior is in the graph, the bigger the dust grains. So in that disk around that star, we have material already starting to grow and forming planets or larger dust grains in the bit that we can see. Now, as I said, there are these events every 31 days. You get a certain amount of material dimming the light, and that changes. So what you can do is for each of these periods, so we just randomly number them from the first one we have observed all the way to 50. And you can, from the duration and the depth of these events, you can actually measure the mass. So the y-axis is simply in arbitrary units, what is the mass that is blocking the light at that occultation. To compare this, 1 in that plot is about 0.03% of the mass of the moon. So it's not a lot of material, but what you can see is basically every time the structure comes back, the mass can be very different. So it can basically go from 0 to about almost 1 here. It can also do that all the way back in the same amount of time. So in 30 days, the material just disappears from that structure, or the structure is completely filled with this amount of material in about 30 days. So the material is really moving about in that accretion disk, not just orbiting, it's also moving about through that structure. Now the question is, of course, what causes this? So one explanation that is usually there is you get an inner part of the accretion disk that looks like that. You have your star, and the inner disk is actually warped up in this direction. That can happen if the star here has, for some reason, a rotation axis that is not the same as the disk. Those things exist. And then what the magnetic field does, it pulls this part of the accretion disk up, and the one on the other side pulls it down. So it will look a little bit like that. And then if you observe, let's say from over here, that part of the accretion disk is blocking the star and the object looks dim, but this thing is orbiting around the star, and after half a period, this bit is over here and this bit is over there. So that would go down after half a period, and we would be directly looking at the star and the system would be bright. Now, we know how far away that object, that structure is from the star, because we know the period and the mass, and that is about 15% of an astronomical unit. So what we know is magnetic fields can by under no circumstances be strong enough to do this. It's too far out. So hence there has to be another explanation to make this structure. The only sensible other explanation is there is a planet in this accretion disk that is already there and has formed, and that planet has an orbit that is inclined to the main part of the disk. And what that planet will do is it will tilt the inner part of the accretion disk in the way in this that's shown in this cartoon from the NASA website. And we are observing this system somewhere from here, and the whole system keeps orbiting. So after half a period of the inner accretion disk, that structure is basically on the other side, and we look at the star directly. If it is in this configuration, we look from the right, the material is blocking the direct light, and we look at this warp. So basically, this is what we think is happening in that system. There's a warp in the inner disk. It doesn't look exactly like this, of course. That is caused by some protoplanet that is there in the disk. So that there's good indirect evidence that that star actually has a protoplanet around it. So we can also look at a second example that looks at a little bit of other signs. Again, in the Pelican Nebula, simply because I like the picture. So this object has this telephone number and it's this star. So the other one was that star, this is this one. What we can do is we can actually accumulate all the data, not just HOYS. So HOYS is basically active since 2016, but we can get the long-term light curve by looking at other surveys. This looks like there's actually a lot of good data out there. And why do we do HOYS if people have done this before? But basically it turns out the red data is from one survey, the green is from another, the infrared from another one, or an accumulation of loads of catalogs. So our data is actually much better. It's all in the same place and homogeneous. And one thing you see is this star shows long-term variability. So every 6 years, there seems to be some kind of up and down here. And there seems to also be a lot of scatter. It was that scatter that we were interested in, because it's actually not noise in the measurements, it's real variation. And the first thing you always try is you see, is it actually periodic? And it turns out, yes, it is. And the period is incredibly short. So this object has a period of just below 20 hours. Basically the light varies almost like a sine function. And this is typically a good sign that there are spots on the surface. And the period that you measure is the rotation period of the star. And the spots on the surface basically modulate the light from faint to bright. What you see as well is there seems to be quite a lot of scatter still around that black line, which is just the sign fit to the data. And you could say, oh, maybe this is just the noise in the measurements. But it actually turns out it's not. Most of this variation, again, it's real because the amplitude of the variation changes over time. And this is basically what we can measure. We can measure the amplitude. So how much does the light vary from faint to bright over time? So these are 4 years worth of data. So these are just number of days on the x-axis here over time. And you see in the 3 filters in the same color coding, when we started, the amplitude was quite high, maybe 0.07 magnitudes. That's about 7% of the brightness. Then it dimmed, or the magnitude lowered. It stayed stable. Then it increased to about 10%, fell down again, and then slowly was increasing. And because now we have all these amplitudes over time at different wavelengths, and this is something that no other survey can do, we can now try to simply calculate, if this is a spot, how big is the spot at each of those times, and what is the temperature? And this is the result if you do this. So the red points here is the temperature of the spot over time in degrees. So you see there are variations of a couple of 100 degrees in terms of the temperature. And this is the area of the spot as it changes over time as a fraction of the surface of the star that you can see. So basically 0.3 means the spot is as big as 30% of half the stellar surface. So quite large spots. And you can see how these spots basically vary over time. That is something that's very interesting. In particular, for that object in particular, we can learn what happens. But what we want to study is basically all the stars that show this. You want to do statistics of that by looking at all the stars, see how these spots basically appear, reappear, how they change in size and temperature. And basically, I have a PhD student starting in 3 weeks' time. And her whole next 3 years will be dedicated to just doing this with all the data that we have, to learn more about how these spots that might come from accretion and other reasons actually evolve over time. So very quickly, if you want to help us by participating in delivering data, most of that you can ask the participants that are already there. But basically, we have a nice, pretty website. There are instructions there. Please read them, pick a target, do some observations any way you like it. Mostly, all we ask is some flat field corrections and image stacking for the same filter for the same night. And then you simply upload it to our server. There's a little bit of processing, but it's not very much to do, and we help out if you can, if you don't have any time. You can analyze the data yourself. So once the data is on the server and you processed it, it's live in a database that everybody in the world can access. That includes yourself. So you can pick any star you want, look at the light curve, download the data, investigate it, and that is up to you what you want to do with it. So we're currently developing some help where I can actually do things like fitting the periods and so forth completely automatically, because that's quite tricky. But you will be able to do that quite soon, and then you get your name on a paper, because that's what we actually do. We're doing the scientific research, and I've highlighted here the 3 people from your society. So there's Barry, Stephen, I don't know if he's here, and Tim, I've seen Tim and Barry being here. And you go with us through the whole process of writing the paper. You have to write up your own section on your observatory. So there's some work involved. It's not just writing along and reading it, but you basically learn about how that process actually works, and you read up the science, because you can read the paper while we are writing it. So that's basically it. That's my last slide. With some contact details. The main thing, just find our website, HOYS.space is the domain, and everything else from there you can find on the website. Thank you.
Wow, thank you very much, Dirk. That's it's truly amazing how much detail you can get out of the information that amateurs can supply. I guess this is probably due to the sheer volume of material that's coming in. There are no questions on the chat screen, but I have one which occurred to me. You mentioned that you can have a planet and an inclined orbit to the accretion disk. Are there any ideas of why a planet would form which has suddenly an orbit which is a different inclination to the accretion disk that it was formed from?
Yeah, there's plenty of ways to do that. The simplest one is if you, I'm just trying to get to the picture, you don't just form one planet, right? The planet formation process, even in our solar system, you form what's called planetesimals first, which is loads of things which are probably asteroid size, things like that. And there's probably going to be, I don't know, 50 to 100 of them in a disk, and they will interact with each other. And they will hit each other and merge. They will interact. Some of the planets might get thrown into the star. Some of the planets might get thrown out, and some of them might just end up in a funny orbit with a higher inclination. So yes, if you just form one planet, it will be in the plane of the disk. But interactions in the disk between the forming planets, that's one way of doing this. Remember, this is a whole star forming region. So there's other interactions with other stars, gravitational pull that might do something like that as well. But typically, I reckon if you got 3 or 4 planets and one isn't in the same plane, it's interactions in the planets. Between the planets itself. You can see that in the solar system, right? We've got a couple of planets which are much more inclined than others. So the plane of our solar system, if you try to observe this, our solar system from the best place to get transiting planets, there's no position where you can get more than 3 or 4 planets actually transiting from the same place, because of all the inclinations of the orbits.
Thank you very much. Has anybody else got a question? There are none on the chat. If anyone wants to unmute themselves and ask a question. Oh, there's one from Gerard. Would you like to unmute yourself and ask your question?
Yeah, hi Dirk. I'm one of your citizen scientists. I just thought I didn't actually remember you mentioning about the LCO telescopes, so it might be worthwhile mentioning that to people. Though you did show one of the screens, you know, sort of how to those sort of graphs about how you sort of get the data from the images. But it might be worthwhile mentioning that you can actually have access to these telescopes online. They're online.
Yeah. So since a couple of months, we actually also have that project open to people who don't have a telescope but would like to use one. I know your society is actually one of the lucky ones to have a whole observatory. But we have time at the LCO Las Cambras Observatory network of telescopes, which we can allocate to people. They're all 40 centimeters, so you got better things in your garden, I think. But if there are people who don't want to actually physically observe, they want to do remote observing, don't leave the house, then you can learn with us how that works. So on the website, there's a whole page dedicated to what you need to do. Just fill out a small form, and then there's lots of emails that you will get from me of instructions. There's videos to tell you how to observe the targets with the LCO telescopes, but then more importantly, how to actually analyze the data. That is basically for everybody. You can learn learn how to analyze our data and do some actually useful science with that. So over time, we will add more of those. It's just been very, very frantic in the last couple of months with preparations of lectures for everybody. We haven't gotten much further, but we will basically put up more videos how to analyze our data and do your own science if you so wish.
Thank you.
Any other questions from anyone?
Yes, I could ask one. What would be the minimum effective size for an amateur telescope to be of any use in this project?
So I get asked that question every single time. Basically, the smallest telescope that we have data from that is useful has a 5 centimeter diameter. So literally anything above that will work. You might have to maybe do longer exposure times. That is fine. And you just don't have the faint stars in your pictures, right? You still get the brightness measurements for the brighter stars in the picture. Then you contribute to that. The bigger telescopes, they go towards the fainter stars that smaller telescopes don't get. So since yesterday, for example, I have 2 weeks of observing time for the project at a 2-meter telescope in Germany. And that will go very, very deep, but I'm getting this maybe once a year, right? So there, the very faint stars we can reach with a 2-meter telescope. And I got the first picture yesterday. It just blows you away how much deeper that is. But basically, most of the stars in that picture, we have no other data for yet. Because typically our stars, the brightnesses go between 10, maybe 16 and 17. Some people go down all the way to 18. Much deeper is no real point because we don't have data for those objects. But the fields are basically picked that the stars we can see in the regions we observe go down to maybe 0.1, 0.2 times the mass of the sun. So we can actually see all the stars that are there in those clusters, right? Anything fainter than that would be brown dwarfs. They were very hard to do. But the target's actually picked that we actually, with the amateur telescopes, we can see all the stars in all the clusters. So typically the sun would be a 15th magnitude star if you move it to 3,000 light years. That is that's why all our objects are closer than 3,000 light years, because the amateurs can easily get to that, even with a small telescope.
Okay, we've got another question from Adrian Wakeford. Why are there so many double stars?
Again, that comes back to what I explained at the beginning, the angular momentum conservation, these spinning things. So basically, literally all the stars form in binaries or even higher multiples. And the reason for that is, if I share my screen again, it might be easier. If you go all the way back in the talk, to that little sketch that I've shown you. Oops, there it is. When you get this formation of the disk, what typically happens is there's so much of this angular momentum in these collapsing cores here that the core will basically split up into 2 stars, and all the angular momentum is then in the orbit of the 2 stars around each other and not in these individual disks. So that's, we call that process fragmentation. So you basically get initially that collapse, but there's one region here that has too much angular momentum, and that will then just break up into 2 cores, which then keep collapsing, and each of them makes its own star, and both of them, they keep orbiting around each other because they formed from that initial gravitational collapse. So all the very close binaries that you see, they're formed either like this, or you already formed the star, and the material that you move inwards, as soon as you move material inwards, you keep adding angular momentum. What that mass accretion process does, it keeps spinning up the star. They rotate faster and faster and faster, and some of them simply break up into two. You're making them spin so quickly that they simply split apart into two, and that explains all these contact binaries, these so-called W-UMA stars, which are basically two stars touching each other. They orbit each other every 6 hours. So their surfaces actually touch, and that's coming from that same process. And that's also the reason all the young stars, they rotate very quickly, a couple of days typically at most. Right, the sun has slowed down over time. It takes a month to go around once. So that's basically where all the binaries or triple systems come from, because they form out of that collapsing core and the angular momentum redistribution.
Okay, thank you very much. There's one other question from Rosemary and Philip Clark. Presumably the dust in the cloud, is that from the breakdown of other stars? Does that mean that the mass of stuff in the universe is constant? And if so, why? I guess the Big Bang comes in here.
That's a whole lecture course. Well, the mass in the universe is definitely not constant. What is constant is probably, the energy is conserved, but cosmologically speaking, not even that. So let's not get into this. Originally, after the Big Bang, yes, you only had hydrogen and helium. You had a little bit of lithium, but that gets killed once you make the first star. So the dust, which I said is graphite, silicate, it's the heavier elements. We call them all metals. So they are made, and they are made in different ways. So there's some nice graphics online that tells you for each element where it actually comes from. So typically things that are less heavy than iron, iron is the 21st element, they come from stars, maybe like the sun to some extent. When they become, at the end of their life, when they run out of fuel, they become red giants. And the core of those stars, they then just fuse the helium that is made from the hydrogen into carbon and oxygen, all the way to iron. That's what the low mass stars do. And during that red giant phase, that material is kind of mixed about into the atmospheres of those stars because it's made in the core. And then it's expelled in the planetary nebula phase to some extent into the interstellar medium. Everything heavier than iron is made in supernova explosions, simply because the fusion stops at iron. You can't fuse iron to anything else. It doesn't work. So all the very massive stars, in particular the very early stars, they were very, very massive, several hundred times the mass of the sun. So they go supernova basically immediately and create a lot of the very heavy elements. So everything heavier than iron has to come either from a supernova explosion or from neutron star mergers. So that's the other way of getting the elements. It's actually extremely complicated for each metal. There's paths in the fusion processes where they can come from. But these are the three main channels. So yes, in our current state, 13 billion years after the Big Bang, we are the third generation at least of stars. So you had the very first ones, very massive, made purely of hydrogen, helium. Then you get second generation ones, which had a little bit of metals, which made from the first ones. And now we have what we call normal metallicity, which is basically about 2% of the material in the sun is heavy elements. Right? The rest is still hydrogen and helium. That's the current clouds have roughly that composition as well, and it's from other stars. Yes.
Okay, thank you. I think we have one last question, which is from Graham Bryant. Is there a typical size of star within this project?
Well, there is no typical star, and this size, using size is always the slightly wrong choice. We use the mass of the star as a better way of talking about them, because the mass of the star determines everything you want to know, and including the size, because size kind of means the physical radius or something like that. there is no typical star. There's a distribution of stellar masses. So there's typically a few high mass stars, and then there's more kind of intermediate mass stars like the sun, and then there's a lot of low mass stars. So the lower the mass, typically the more of those objects there are in each randomly picked sample or star cluster. So all the way down to maybe 10% of the mass of the sun. You get more and more low mass stars. So the sun, technically speaking, is a high mass star because there's only, I think about 5% of all the stars in the universe are more massive than the sun. Astronomers still call the sun a low mass star, but you could also say it's actually a high mass star because 95% of all the other stars are lower in mass. So it depends on your interpretation. But typically, the objects that we see, they're about, the average star is probably half the mass of the sun. So if you want to if you pick a random star in one of the clusters, it's going to be a half solar mass star, most likely. That's probably the best answer to that question.